You should be clear for liftoff.
Let's not go over 20 minutes or so.
Okay. Yep, you're good. Whenever you're ready.
All right, roll 'em. It's already on?
Yep. You're rolling.
Welcome to part 3 of magnetic fields. This can be found in your text in chapter 29 for the new version, chapter 30 for the old version. What we're going to do today is to talk about magnetic fields that are caused by current carrying wires. Now, up until now, we've been talking about putting wires and charged particles, moving charged particles, in external magnetic fields. Today, we're going to talk about the currents and the magnetic fields that they cause. And what I want to start with is the law of Biot Savart. He was the first to quantify the relationship between currents and the magnetic fields that they produce. Remember that Oersted did the experiment where he found that a current-carrying wire produced a deflection in a magnetic compass. But Oersted was the first to provide a quantitative treatment of magnetic fields and currents. So let's start with that. Let's talk about if I have a wire carrying a steady current I going in this direction, I can talk about some teeny piece of that wire. We'll call that ds. And what we may want to do is find the magnetic field due to the wire at some external point P. It's going to be some distance r from the wire. And we have the unit vector r to indicate that distance. We have the angle theta to indicate the distance between that particular current element and the r unit vector. And so this is what, at least qualitatively, what we have found. First off, if it's a constant current, we found that the magnitude of the magnetic field was proportional to that current. The field was also proportional to the sine of the angle. Also found that the field, that little piece of field due to this little piece of current, was perpendicular to ds. And then finally found that it was inversely proportional to r squared. And if we put all of these things together, we have this nice relationship between this piece of current causing a magnetic field at P, the value of that current, and the field itself, and we can write it in this way. mu naught times the current, again, we're assuming a constant current, over 4 pi times the integral of ds cross r unit vector over r squared. And this is the law of Biot Savart. If I should say this is, write that as an integral form so that we can say the magnetic field is equal to mu naught I over 4 pi ds cross over r squared. Mu naught is defined as the permeability of free space, and it's equal to 4 pi times 10 to the minus 7 Webers per amp meter. It's a constant similar to the epsilon naught that you remember from electrostatics. In fact, there's a very nice relationship between epsilon naught and mu naught that we'll get to later on in the course. If we want to find the field due to that entire piece of wire, what we do, of course, is integrate, and then this is what we have. Now, the interesting part of this integral is you have to be a little bit careful because there's a cross product in the integral. And so our result will be in vector form, and we want to be a little bit careful about that. You'll notice, though, that the Biot Savart law is analogous to Coulomb's law for electrostatics. So in the case of the Biot Savart law, B is proportional to I, whereas in the electrostatic field, the electric field was proportional to Q, the size of the charge. Both B and E, the electrostatic E, are proportional to 1 over R squared. So they're both inverse squared force laws. So the nice thing about Biot Savart law is, assuming that you have decent symmetry, you should be readily able to calculate the magnetic field at a point due to any current carrying wire. And so what we'll do at this point is do an example, and this is a rather complicated example, so I'm going to try to go through it carefully in terms of calculating what you would think would be a simple problem, the magnetic field due to a long straight wire. Actually, it will be a simple problem later on. So here's my long straight wire, and here's my origin. I want to find the magnetic field. Let's assume I have a constant current I going through this wire. I want to find the field at some point P. Let's say that it's a perpendicular distance of A from the wire, such that if I go to this end of the wire, I'm going to use R as my distance. I'm going to call this angle here, I'm going to call this angle phi, and I'm going to call this angle theta. And you'll see why I'm using two angles in a moment. So using right-hand rule, what we know is that if I have a current going in this direction, I put my thumb in the direction of the current. My fingers are going to wrap around the wire like so, which means that the magnetic field at point P is coming out of the board. So the field is going to be going in the K direction. That will be the resultant of ds cross R, if you will. So immediately we know that I can write ds cross R, remember, is a unit vector, has magnitude 1. It's just going to be in the K direction, and it's just going to be equal to, we'll call that dx times the sine of phi. Very nice. One of the problems with this is, though, that when I want to integrate over the length of a wire, it often makes more sense not to use this angle phi, but to use this angle theta, so that I can use that to sweep across the length of the wire. And so I'm going to write this as k dx times the cosine of theta. They're complementary angles, and so I can use this expression. And I'm going to be much more comfortable using cosine theta for my angle. And then I'm going to, what I need to do then is to put this all into the Biot Savart law. When I do that, I'm going to write B then is going to be equal to mu naught times I over 4 pi. Let's see, we said ds cross R is going to be dx in the K direction, cosine theta, d theta divided by R squared. Now you'll note immediately from this that we have several variables to deal with. We've got a theta, we've got an R. The other things are constants, but we can get these guys, and we have a, I'm sorry, this should be a dx. That being the case, we're going to have to write two of the three variables in terms of the last. And so we're going to do that in this way. We've got three variables. We have dx, we have cosine theta, and we have R. I can write R immediately as, I can write R squared as A squared plus X squared. I can write A over R as the cosine of theta. I can write then R as equal to A over cosine theta. if I look at the diagram, I recognize that tan theta can be written as x over a. So therefore, x is equal to a tan theta. Dx then would be a secant squared theta. So we have a rather a big mess. We're going to put this in the integral, and you'll see that immediately, while it looks messy, some terms will drop out, make our lives very simple. So all I've got is mu naught I, k direction over 4 pi. I'm going to integrate from theta 1 to theta 2. We haven't specified an angle, but we can later on. And then if I put this all in, I get a secant squared theta times cosine theta times d theta times cosine squared theta over a squared. This accounts for my 1 over r squared. So I put all this together, and lo and behold, I have secant squared times cosine squared multiplied together. That's going to give me 1. And I'm going to end up with a very simple integral that looks like mu naught I k over 4 pi. And that's going to be integral divided by a cosine theta d theta from theta 1 to theta 2. Simply, I integrate cosine theta, I get sine. So it's going to be mu naught I k direction 4 pi a sine theta 2 minus sine theta 1. And so that's the expression for the value of the magnetic field at point P due to this long current carrying wire. We can do a special case of this where let's let theta 1 be 0 and theta 2 be pi. So in other words, an infinitely long wire. If we do that and put my limits in, theta, then I'm going to have, that will give me that b is equal to mu naught I over, and I'll get, when I do that integral, I'll get 2, which will give me then mu naught I over 2a in the k direction. So this is for theta 1 equal to 0 and theta 2 equal to pi. That will work out very nicely. Okay. We can do a somewhat simpler example of this. Where we have, suppose we have the following situation. It's kind of like a baseball field. But I have a current going like this, then like this, around this, down this way, out this way. And let's say I want to find the magnetic field at the origin, at O. Let's say this is a constant distance r, capital R. We can break this into several parts. First off, the line segments OA and OC are both such that the current and ds are parallel. When that happens, that means that ds cross r will be 0. So these two lines provide nothing to the magnetic field. In fact, these lines are both parallel to, both ds and r are going in the same direction along these paths as well, and so the field due to this part of the wire will be 0. So in other words, the only part of the wire that contributes is this curved path up this way at a constant distance r from the origin. So let's write out, I can write my Biot Savart law as mu naught I over 4 pi, pull the r squared out of the integral because it's a constant, from 0 to some distance s, integral of ds. Well, ds is the length of this sector of the circle. It's much more easy to express this as r d theta and let theta go from, again, theta 1 to theta 2. This becomes a very simple integral. The r cancels one of the r's in the denominator. I end up with mu naught I over 4 pi r theta 2 minus theta 1. If the current is going in this direction around the loop, that must mean that the magnetic field is into the blackboard, which is what we would expect. We'll do one more example of using Biot Savart law for magnetic fields. And that's the following example. Suppose I have a circular current loop of radius r, and it's located some distance r from a point along the axis. Okay, so little r is going from the center of the loop out to this point P where I would like to measure the magnetic field. R I could write in this case as r squared plus x squared, where x is the perpendicular distance from P to the circle. So once again, I can write my magnetic field as mu naught times I over 4 pi r squared integral ds cross r. I can write this as mu naught I integral ds 4 pi x squared plus capital R squared, which are both constants. That being the case, I can in fact let x be the perpendicular distance, let r be the distance from some point on the current loop. That makes more sense. If I write it this way, I'm going to find that if I break the magnetic field into two components where I can talk about the field that's along the x direction and the field that's perpendicular to the x direction, I'm going to find that all of these components add to 0. Because for every component I get at one point on the ring, I'll get the current loop, I'll get an equal and opposite field contribution perpendicular from the other side. Kind of like the ring of charge that we did back when we studied electrostatics. B sub x then I can write as ds. So if I want to find B sub x, I'm going to write that as mu naught I over 4 pi x squared plus r squared times the integral of ds cosine theta But notice, theta, x, and r are constants for all elements on the loop. Therefore, immediately, I'm going to get that my field is equal to mu naught times I times a squared over 4 pi, capital R squared over x squared plus r squared to the 3/2, where I have written cosine theta as r over x squared plus r squared to the 1/2. So that is my magnetic field. Very similar, if you look back at your electrostatics chapter, very similar to what we did when we studied the electric field due to a ring of charge. At the center of the loop, where x is 0, the field becomes very simple. At the center, x will be 0, so the field will be mu naught I r squared over 4 pi r cubed, or mu naught I over 4 pi r. We'll leave that for now. We'll come back to this. We'll move on to magnetic forces and then Ampere's law in the next lesson. Thank you.